All right. So I think, like maybe I should spend some time talk about quiz 1. I think the deadline is over, right? Let me double check before I start that. So quiz 1 was, 2 days ago, right? So we're all done. How did you all feel with quiz 1? Was it too easy? Was it too confusing? I think like some of you had differences between what you read in OpenFlow spec and what I taught in class. I'm just pulling up the questions. So I guess I have 44 responses, so that's pretty good. Right. And we have, I think most of you have scored very well. That's good. So let's start, maybe we can spend some time, few minutes, talk about some of those questions, especially the ones that were confusing. And, I can try to clarify everything for you. So I'll start with the one that I think Garrett figured out is problematic. So maybe I can start with that. That was, I guess, the second last question, right? So yeah, so the last 2 questions were mostly confusing, but I think like some of you were confused on other one as well. So the second last question was, what happens when a packet's header matches 2 OpenFlow's match action rules, right? And there was a bit of a confusion on this one. So, I think I had this option written down incorrectly, which is, action for more specified rule is applied even if it has low priority. But OpenFlow specification does not say anything about more specific. So I kind of confuse the more specific with the exact match rules, right? So there is a difference between rules being more specific and rules being exact. And the OpenFlow specification kind of focus, in general focuses on prioritizes exact match rules. But I think in general, if there is any type of discrepancy between rules, then the priority bit is the one that is used to figure out which rule should be applied on the packet. So I have in some sense canceled that question. I'll be canceling that question and updating your scores accordingly. So thanks for picking up on that. What else? The second, the last question, right? So what happens to a packet that does not match on any OpenFlow rule in data plane? So there's a difference between what is a best practice versus what is written in the spec. So what I was telling you is kind of the best practice that if you don't have any rule that or any match for the packet, then you send it to the controller, and controller basically figures out how to handle that. But technically, you can specify the action OpenFlow, forwarding to controller is also an action, right? So that's kind of a default action that most practitioners use, but you can also apply an action where you can, use any of those action primitives and maybe forward some random port or maybe drop it. It's up to the programmer to specify what actions to apply. Okay. So I guess the option was not convincing in this case as well. So we'll have to cancel this one as well. But I think I was glad to see the persistence and kind of the intensity that most of you had, that you followed up and saw the spec and everything. So that's encouraging. But are these explanations clear now, or is there anything else that we should talk about and clear out confusions if you still have them? Chat. Yes, no? Can we move on? Anything else that you folks want to discuss about the quiz? Okay. You can see my screen now? Okay.
Yeah, we can.
Okay, perfect. So I think, before I move, I just want to clarify that, some of you might be getting a bit confused about the lecture order or the lecture number in slides not matching with, our current order. So the reason is that I'm trying to slow down the content a bit. So I'm, whatever I was initially planning to cover in one lecture, I'm trying to take, more than one lecture to cover them. So I'm now maybe breaking them into modules might be more appropriate rather than calling them lectures. So I'm kind of like, I will update everything else that is already on the website. But I think like the important thing here is that maybe it's not a good idea to run too fast and not understand anything. Maybe we should take some time and try to learn less, but try to learn it well, right? So with that, let's get into this network operating system part of the module, which is focusing on the network operating system, right? So before we do that, let's try to recap that, forwarding abstraction requires data plane. Like last 2-3 lectures were focusing more on the programmable data planes. We talked about the data planes can be implemented in the software or in hardware. The software data planes, the most popular ones are OVS or Open vSwitches. These are very flexible, but they're slow. Hardware data planes, which conventionally are all fixed function, are fast but inflexible. And then the more recent generation of hardware target is called PISA. PISA stands for Protocol Independent Switch Architecture. It tries to strike a balance between flexibility and scale, right? So it is relatively more flexible than fixed function switches, and it is faster than software switches in terms of packet processing, right? But it is not as flexible as CPU. And speed wise, I think like it is okay. And like with all the recent advances, like speed wise is not too much of a compromise, but it is trying to offload some flexibility into the hardware target without slowing the pipeline down, right? All right. So with the operating system, we are going to learn about what are the different type of network operating systems, and people use it as a replacement for SDN controllers. So the confusion that you might see where network operating system and SDN controllers are confused between each other, that is more because that this abstraction, the clarity of abstraction evolved over time, and people just use a lot of terms and jargons which are not really motivated well, right? So we will stick with network operating systems, but if if I for some reason end up saying SDN controllers, then we should consider that as a network operating system. And if there is any other nuance that needs to be discussed, I'll cover that as we move forward, right? What are the scalability challenges for these SDN's control planes, and how different network operating systems address these scalability challenges, right? So this will be kind of like the key focus that we will have. We will dive a bit deeper into ONOS and Onyx in today's lecture, or hopefully in today's lecture. But we will do a, so the version of ONOS that I'll talk about is the original version of ONOS that was introduced early in 2014. And in next few lectures, we will talk about ONOS current version, where the software stack has evolved a lot, but the focus has more switched towards these reconfigurable targets, that is the PISA targets, right? So when ONOS was designed, it was designed from open flow in mind, but things have changed and evolved a lot in past 5-6 years. I think like ONOS came out in 2014, or the research paper came out in 2014. So it has been 7 years, and the industry has massively changed in past 7 years. So we will look at the new version of ONOS and try to calibrate our expectations of how things have changed and evolved over time. Okay. All right, so let's try to recall what network operating system means when we think of software-defined networking. We have host, we have the network, we have a software data plane, we have a hardware data plane, and then the network operating system is the one that is responsible for interfacing with these forwarding elements in the network, and then provide the abstractions to the upper layers, right? So the interface or the APIs that are used between the network operating system and the data plane is called southbound API. And the key thing that network operating system is providing or is offering to the upper layers is this view of the network, right? When we ignore the virtualization, then it is the physical view of the network, but then you can think of a virtualization layer that can provide a virtual view of the network. But the goal of this network operating system is to, like worry about all the mechanisms through which it can realize this abstraction. It can offer this abstract view of the network to the control programs or the upper layers here, right? And the interface, as we know, that is between the operating system and the control apps is called the northbound APIs. Okay. All right. Network operating system. So network operating system can be a distributed instantiation, right? Or it can it is a centralized abstraction, but it can be implemented as a distributed system, right? And let's soak that in, right? Because this might be a bit confusing and overwhelming to understand that we're arguing for centralization and then we're talking about distributed system, right? So let's try to understand the nuance here. So the network is, distributed set of forwarding elements that we have, right? In the previous generation of networks, the control plane and data plane were all integrated into one device, and the control programs were all responsible for maintaining this distributed state, right? So if you remember this RFC that we have been referring to, we talk about OSPF. It only takes 3 or 4 pages to explain how OSPF has to be realized, but hundreds of pages to explain, or 100+ pages to explain how this distributed state has to be maintained so that the control program can apply the Dijkstra algorithm for shortest path, right? But now what we're talking about is that from a control program perspective, we want to provide a logical centralized view, which is like, for this program, everything is centralized in terms of control, right? So it can program any device it wants as a program, but that does not change the distributed nature of the problem away, right? Or like it does not take away that challenge away, right? So the network is still distributed. So either when you have a physical centralization and logical centralization, which means that there is only one device, one server that is acting as a network operating system, that is a physical centralization, that all these distributed forwarding elements are only talking to one server, then that is a centralized implementation or centralized realization of a centralized abstraction. Okay. But it is possible that you can have a distributed set of or of servers which which are all running different instances of the network operating system. To the control program, it is still providing a centralized abstraction, but realization can be as a distributed system. Okay, so let's take a pause here and make sure that everybody understands this concept. Any questions? No questions? Okay, I was confused the first time when I learned about SDN, and I was confused about, hey, when everybody says centralized abstraction and then they start talking about distributed systems. So I was totally confused about what does centralization really means. So I'm glad that nobody is confused, or maybe nobody is interested enough in figuring out what this nuance is. But the takeaway message for you is that what we are offering, or what software-defined networking is offering, is a logically centralized system. But that does not mean that it has to be implemented in just one physical server, right? So you can use a cluster of servers to realize the network operating system. That does, we are not really forced to implement network operating system in one physical location or one physical server, right? And this might sound a bit counterintuitive, but as we will discuss further, it is very important from scalability perspective, right? Think about a network as big as Google, which is geographically distributed across different locations around the globe, right? Can we imagine having just one centralized server which is responsible for providing this control of providing this operating system, or this one server which is responsible for all these set of network operating system operations? That is hard to imagine, right? And that is the kind of motivation for that. Yes, we have taken away this abstraction. We have removed, we have decoupled software, the data plane and the control plane. But to provide that centralized abstraction, we are not required to have just centralized realization, right? The realization can still be distributed, but it is you have to note that this is a distributed operating system, right? The logic the complexities and everything is sitting in these servers, right? Not on those devices. So the argument that we had that, why do you need to take the control plane away from these forwarding elements is because now we can afford to keep them fast and dumb and have the intelligence somewhere else, right? So this is the kind of like argument for distributed instantiation of centralized network operating system for networking. Okay. All right. So network operating systems, as I was saying, like we can have these instances that are managing or are just interfacing with a subset of forwarding elements rather than interfacing with each and every forwarding element. And when I say forwarding element, I'm talking about all the switches, routers that we have in the network, right? So this also includes the software data plane targets such as OBS, and also the hardware targets that we have in the network. And when we have these network operating systems that are, like interfacing or exchanging information with each other, the interfaces, the application interfaces that we use to share information between these operating system instances, we call them east or westbound APIs. Okay, so between operating system and forwarding element, we have southbound APIs. Between operating system and control programs, we have northbound APIs. And between like different operating system instances, we have east or westbound APIs. All right. So now let's talk about the scalability challenges, right? So we have the forwarding element, which is maybe responsible for handling packets 100 to 10 to 100 Gbps. And we know, based on some of our discussions in the past, that the latency that we're talking about to the packet is of the order of nanosecond, right? But now if I am, if I'm offering or if I'm forcing these packets to go into the network operating system, then I'm adding an additional delay, right? And the reason why this is going to happen is that switches have limited memory in terms of TCAM or SRAM, and then a lot of time the network operating system might be responsible for handling packets in the user space, right? And this is related to the quiz question that we were discussing, that because you have limited entries in the, or you can only support limited match action table entries in the data plane, then a lot of time when the packet is coming in, you might not have a matching entry. And the default logic that programmers apply, like they don't want to drop those packets typically. Technically they can, but they don't. So they forward that packet to the controller or the network operating system. And then network operating system is like required to figure out, maybe it has its own internal logic, maybe it has a cache of rules that it has already pre-populated and it pushes those rules down, or like it on the fly computes that what should be the forwarding decision for this specific packet, right? So there are multiple things that the network operating system can do, but basically what we are talking about here is that we have to send the packet from data plane to the user space for further processing if we don't want to drop packets, right? And then from nanosecond delays, we are talking about microsecond delays, and given like for a fixed amount of compute that can lead or that can significantly bring down the throughput to 10 to 100 Mbps, right? Compared to hundreds of Gbps that we can support in the data plane. So packet processing in user space is slow. And this is the reason why we desire a lot of flexibility, but we don't have software routers in the core, right? And now you might be wondering that, hey, we talked about these open V switches. So if we can implement those virtual switches in software, then why can't we implement them anywhere else in the network, right? So is that a question that comes to your mind? That when we learned about open V switches. Open V switches can run in the host. Then why can't we implement these intermediate forwarding elements in the software as well? Does anybody want to take a crack at that question? That why don't we use software switches in the core of the network? Okay, so one question answer is that like our virtual switches only for virtual machines? Technically, no. I can implement them for, like I can build a software switch, right? And I can implement them. They're not necessarily tied to virtual machines, but that's how they're used. So Kevin's response is slower due to pure software implementation. Yes. So we were discussing in the last lecture, or maybe last lecture, the differences between software data planes and hardware data planes. The difference is that it takes a lot of CPU cycles to process a packet in user space, which means that one, we will be spending a lot of resources handling those packets at scale, and then like things will be slow, right? So we are talking about order of microsecond delays for packet at every link, right? That's not a very desirable thing. Okay. And for what it's worth, I think like the networking community has evolved or has been debating on this question about hardware versus software, because like software means that you can like treat it as a non-networking problem, right? You can treat networking as a software problem, right? And that is in some sense the goal of software-defined networking has been, but taking away those forwarding elements or taking away that hardware completely makes network a bit more liberating from a software perspective, right? And for what it's worth, there have been multiple startups in this area where they just envisioned a future where we don't have any hardware switches at all, right? And we just have software switches in the network. And their argument was that, hey, CPU is cheap, so we should just keep pushing it. But as we have discussed in the past, in like if you remember lecture 2, we were talking about the difference in like the processing speed for CPU versus hardware targets. There is around an 80 times difference, and that gap is kind of like significantly growing. So even though like you can argue that yes, I can replace everything with CPU based devices and CPUs are cheap, but I think like economically it has not made a lot of sense, right? And now I think like the other side question that you might have is that, okay, if if software is such a problem, then why are we using it in the end host, right? So why are we using it on the end host as open vSwitch, right? So why don't we use hardware there? Any attempts to that? Like if software switch is a problem, then why do we use it at the end host as OBS that we were discussing in the last previous few sections lectures? So is the question clear? My question is that if software switches are so undesirable, why do we use them at the end host when we are trying to provide networking or connectivity for these virtual machines? I think all these answers are correct. So one, because we're trying to provide the like virtualization abstraction, so some logic has to be there on that physical server to route the packet for different tenants out of that server, right? So that is why we need something inside that server. That is one logic, right? But even inside that server, technically I can use a hardware abstraction, right? So I can connect that, or I can provide that routing through the network interface cards, or offload a lot of switching logic to the network interface cards, right? And like we will discuss that in the future, but programmable network interface cards is still an evolving area of research, right? So like network interface cards are not as programmable as a typical pizza switch that we have, or not as performant as a typical pizza switch as we have. So even though we like we are forced to do something on that physical server, but we have an option of still using an hardware which is in the form of network interface card, but the cost balance is still not there yet. It will happen in the future, and there is a lot of research going on right now where people are trying to figure out that like how should I design the architecture of these network interface card such that I can provide most of what Open vSwitch is offering. In fact, there is a research going on, or there is a chain of research going on where people are not just thinking about offloading the logic of these switches, but they're actually thinking of offloading the logic of TCP itself, right? So from 176A, you know that TCP is like making all these decisions about congestion windows and how many packets it should send in any window. So all that congestion control logic, people are actually thinking about how they can offload that into the network interface card, right? So like the takeaway point for you is that there is a strong motivation to not do any type of packet handling in the CPU or in the software switches, because everybody is using these CPUs for a wide range of compute tasks. So they are motivated to not waste any CPU cycle in handling packets and offload as much as possible to the hardware targets. But there have been fundamental challenges in offloading these tasks to the hardware targets, right? So these programmable NICs or programmable network interface cards, which is the next generation of like hardware targets, if you can think of them, are like that is still an evolving thing. I don't think the community has converged exclusively on like, okay, these are the targets that are best suited. But if you go to Microsoft, if you go to Google, Amazon, everybody is looking into this specific challenge of how can we offload packet handling to network interface cards in a programmable manner such that it is offering the same level of flexibility which Open vSwitches are offering, but at a higher speed with lower CPU overheads. So Garrett has a question. I don't know if that's recent one when I'm just looking at it. So travel from user space to data plane and then VM would be slower than yes. So like it can be, it cannot be, right? So if you're using these NICs, then you can avoid a lot of that, right? So you can actually bypass kernel and you can directly like switch or like move the packet from user space directly to the NIC and back. So you can avoid a lot of those overheads, and that's the kind of like focus that the research community has these days in terms of minimizing the overheads of moving packets across different VMs on the same physical server without relying on Open vSwitches, right? And there's actually a very interesting research paper, if any of you are interested in, at SIGCOMM last year, which talks about the overheads of different software stack that we have on the server for handling packets. And it basically argues that maybe we have been doing everything wrong because like the software like even Open vSwitch is implemented using like the existing kernel APIs, right? So like everybody assume that those are all efficient and we don't need to change them, right? But now with these given unique requirements that we have from networking perspective, people are thinking that did we make the right assumptions about what type of APIs should we be using? Should we be using like engaging kernel at all in handling packets, or should we be bypassing kernel completely when we're talking about packet handling, right? So these are all interesting research questions that are out there in the community. I don't want to bore you with my excitement about all those things, but I just want to give you a perspective that software switches are desired because of their flexibility, but a lot of time it doesn't make sense to use them, especially when we are talking about the core of the network. But like software switches are okay, or kind of like a good compromise right now for the end host programming, especially when we are talking about these multi-tenant data centers. But I think like the future will be something different. And like 3 years later or 4 years later, when I'm maybe teaching this course again, I might be saying different things and saying like, okay, we don't really need to learn more about OVS because it's a dead thing, right? So that is a possibility. That is a possible future out there. All right, so let's get back to the original set of questions that we had. That now we have a sense of distributed instantiation, centralized operating system. We know that we might be requiring eastbound or westbound APIs to interface between different network operating system. And we know that like the network operating systems have a scalability challenge because of the limited TCAM. They might not be able to handle each and every packet coming into the hardware target, and some of those packets have to be sent to the user space and have to be handled by either the network operating system or maybe by the control program itself, right? So none of those situations are desired. So like what can we do, right? So let's try to understand the challenges, the scalability challenge from two perspectives. One perspective is that if we have like a single instance of control plane, or when I say control plane, like network operating system, if we have a single instance of that, then we are either stressing the resources that we have on the controller. That is one challenge. The second challenge is that we are also stressing the control channel, right? So when I say control channel, you can think of that as the southbound API, right? So the interface that is connecting the control plane of the operating system to the data plane, it has a limited bandwidth, right? So like if I have a switch that is capable of handling total 3.2 Tbps of traffic, I might be talking about maybe 10 Gbps of bandwidth that I have between the control plane and the data plane, right? And if there is so much of traffic coming into the switch, and if I have to handle almost half of those packets, or 1% or 10% of those packets, I'm talking about a significant overhead and significant flooding of this control channel, which is an immense scalability challenge, right? So in general, like this is like, if we go with this naive approach of just using one physical server as a control plane, then we are either stressing in terms of the resources that we have on the controller, or we are stressing the control channel, that is the communication channel between the operating system and the data plane. So what can we do? One approach is that we do this naive or simple distributed network operating system, that we like run multiple instances of the operating system on different servers, and only a subset of data plane elements interface with one operating system, and the other interface with the other instance of the operating system, right? And this is how two very popular operating systems that we will be talking about are they are implemented. I would correct that like there are more nuances to it, but at a high level we can map this simple distributed abstraction to Onyx and ONOS, right? And we will talk about Onyx more, but I just want to give you some perspective that Onyx is not just an academic prototype, right? So Onyx was, like OVS, was developed in the open source community. The initial version was called POX, and then from POX it evolved to Onyx. And like Onyx was pushed a lot by the open source community, but embraced a lot by Google and a couple of other enterprises back then. And they had dedicated teams which were interfacing with the open source community to build this robust, reliable operating system which they then deployed in their own network, right? So Onyx is not just an academic pipe dream. It is actually a real system that was developed over multiple years. I would say it took maybe 4 or 5 years from like inception to execution of Onyx and getting it deployed at Google. And we'll learn a bit more about it. Like, it's not a perfect system. I don't think Google uses Onyx right now, but it was the initial set of operating system. These are all initial set of ideas people had about how to design an operating system for networking. Okay, if you have these different instances, then you will be able to reduce the controller resources, but the control channel might still be stressed, right? Because we are still sending too many messages to these servers, and like they might still be facing challenges in handling those type of information, and also like saturating the link capacity that we have for this control channel. Okay. So the alternative approach that people started exploring was to have a hierarchical design, right? So in the hierarchical design, what they did was that rather than having a flat structure for how you distribute this, maybe you can distribute it where like there are these different layers, and you have a lower layer which is handling like the low level information, and then it is processing that information and then serving it to the higher layers, right? So this you can think of a hierarchical decomposition of network operating systems. And there was a research artifact called Kandu, which was basically implementing these set of ideas. It had a lot of challenges which made it not really realizable in practice, but it was a good academic exercise to explore the design space and think about what if we have this hierarchical abstraction for network operating system. And I would say that like a version of Onyx kind of like adapted these hierarchical control design itself. So I think like when Onyx published, they were also talking about hierarchical network operating or hierarchical design, but like as a principle, I don't think they had an implementation of it back then, right? So these are all the ideas about how we can scale the network operating system. And then the other idea was that maybe we can offload these processing to the switch itself, right? So because if you remember, the switch also has an operating system. Even though we have reduced the amount of compute resources that we spend, like on the switch, but still, like it's a CPU, it can do few things, right? So the idea that a lot of people had was that, like the CPU is sitting there, and if we can use it to handle all the local events that don't really need to be processed or reported at the upper layer, then we can significantly reduce the the stress on the control channel. And having that distributed design is already solving the controller resource problem. So then we will have a much more scalable design out there, right? So there were research papers called DFAN and DevoFlow, which basically built upon these ideas. They built some real prototypes, and all these ideas were kind of like adapted and absorbed by the open source community, and kind of like the resulting system had some pieces of these ideas embedded in it, right? All right. So we'll now take a bit of a deeper dive into some of these scalability approaches, and I think we'll focus more on the realizations from Onyx perspective. As I said, like Onyx was a distributed control platform developed at Google, and it had these nice abstractions that it used, which is, from learning perspective or system design perspective, it's a good read. I have the reference. I think on the website, I incorrectly says that it is a required reading or something, but like don't worry about it. You're not required to read it, but you're more than welcome to read it, right? So Onyx has this view of network components that like we have the physical infrastructure, which is these switches, routers, which I've been calling as forwarding element, but like basically we can intuit that as a physical infrastructure as well, right? And then it had the connectivity infrastructure, which is the channels for messages. And then it has Onyx, which is the instance that is a distributed system running the controller. And then it has a control logic, which is the network management application that are running on top of Onyx, right? So now you see that the language that we have been using, there's a bit of a difference between what we have been using versus what specifically Onyx is using. And if you try to read any of these research papers, you will see that different papers are talking about or have a completely different taxonomy for the same thing, right? And this is just a sign of evolutionary nature of this area, that not everybody has, like, right now we can go back in time and say like, okay, this is the right abstraction and these are the right taxonomy to use. But as we were evolving, nobody really had a very good sense of, or like, I won't say that what they're using is incorrect. I'm just saying that like people can come up with different taxonomy for the same thing, right? And that's a very natural thing, and that's how evolution happens. But now I would say the community is more or less converging on the right taxonomy to use, and like whatever we have been using, I think that is more in line with what the community is using right now. Okay, but I just want to highlight that you will face these differences in terminologies and jargons in the context of software defined networking. You'll see different taxonomy for the same thing, and that's because the area is still evolving, or at least these terms were coming from the time when area was still evolving. Okay, any questions? Okay, no questions. All right, so let's try to take a look at the Onyx architecture. So Onyx had these like the switches, which are basically the physical physical infrastructure. Then we have the connectivity infrastructure, which is basically the connection between these data plane elements of physical infrastructure and the operating system. And the operating system is implemented on servers, like different instances of the servers, and different set of switches are communicating with a different set of servers out there. And each of these servers are implementing like this import and export of information through the southbound APIs. And there is the east-west bound APIs, that is the distribution of information across different instances of the servers, and each of them is offering a network information base. Now this network information base is important because that is the core of the distributed state abstraction, right? So distributed state abstraction was that's provide a simplified, logically centralized view of the network, right? So what, like that view can be a graph, can be a database, right? So you can view this nib as a realization of that graph or database, right? So it is called network information base, nib, right? And that is the one, like this database is the one that is exposed to the control programs, right? So control programs are sitting at the top, and those control programs are accessing this network information base, and based on that, they're applying the logic of, like how to read any type of changes in the network, and then how to apply their policies, control policies in the network. Okay. Any confusion so far? So this network control logic is another term for, the control programs or control application that we have been talking about, right? And this nib you can think of as the global network view, like the network graph or network database, which is the graph that is exposed by the network operating system to the control programs. Okay. So Onyx abstraction wise, it is offering a global view that observe and control a centralized network view through nib, which contains all physical network elements, right? So note here that Onyx is not offering any virtualization yet, right? So a virtualization layer has to be added on top of Onyx so that the control programs actually work on a virtual view of the network rather than the physical view of the network. Onyx is offering a physical view of the network, but it is offering that as a network graph or a network information view, network information base. It has this notion of flow. The first packet and subsequent packets with the same header are treated in the same way, and they're called as, like, or they're termed as flow. Which offers the the match action style forwarding abstraction, which is amenable to open flow realization. And it is event-based operation, right? So, or it offers this event-based operation that the controller operations are triggered by routers or applications. So what does that mean, right? So let's talk about the events in the network. Can anybody tell me a bit about, what is your intuition about events in the network, or what type of events happen in the network? Okay, I missed some of your questions. So yes, so somebody says, let's follow up on this, and I'll catch up with the other questions. So nodes going down, yes, that is an event. What else can be an event? So nodes can go down, but also can the links, right? So the links can also go down, right? So you have a network device, either the device operating system fails, right? When I say device, think about a switch. So switch does have an operating system, we know. It fails and it is not able to do anything, right? Or everything else is working, but just one port is down, right? So that is a port specific event. And then there are these links that can go down, right? So there are different type of events that can happen. And like all these things that we are talking about are failure related events, right? But there can be events about link utilization as well, right? So, there is no failure, but there is, maybe you can set a threshold and say, like, if the utilization goes beyond 50% or 90%, then send me an event as a controller, and then I want to react to that and change my forwarding policies, right? So that is the link utilization is also an event that needs, or that can be reported to the controller. Okay. So there is a suggestion that, is packet sending an event? We can treat that as an event, right? That, if you're starting a new flow, you can treat that as an event. Most likely you will have a flow entry for it, but it is also possible that you will not find that flow entry, and then you will be reporting that up to the controller or to the operating system, and that is also, you can treat that as an event, right? So you can program saying that, like, every time I see a new flow, send the first packet to me, right? And that is also an event that the controller can have, and so that it can maintain, say, a view of what are the active flows in the network, or how many total flows are there in the network, right? So if it wants to maintain that type of state, then it can program the network and say, like, first packet of a particular flow, just send up. I want to see what headers it has, right? So we can treat that as an event. So going back, there were some questions, right? So there was a question about nib. So I think that is clarified. And there's a question about difference between virtual and physical view, right? So recall that in our previous lecture, or first week, we were talking about the virtualization and we were talking about these abstractions, the control specifications that we have. The control program can either operate on a physical network, right? So, like your network operating system is providing a network graph. That network graph can be a physical network graph, which is like, the actual devices that you have, or it can offer a virtual view of the network, right? So, for example, a control program only cares about, elements in one location, right? It does not care about like, the switches in other location. It only cares about switches in one location. Then it can be offered a virtual view where it only sees these switches and nothing else, right? So that is a virtual view of the network, right? So there are multiple use cases that we can have, right? So we discussed about the tunnel that is offered between the end host in the data center, multi-tenant data center cases. So like the forwarding pipeline between these end hosts, you can, treat that as one big link, right? So that is another way of like, virtualization that is possible, that you don't care about the core of the network, you just look at these edges, right? So that is a view of the network that is offered to the control program. Control program can write things assuming that like, they're all connected to each other as a single hop, right? So this is the difference between physical view versus virtual view. And we'll cover the virtualization in more detail in next few lectures. But I think, I just want to make it clear that network operating system as is not responsible for virtualization. Virtualization is a layer that can be added on top of network operating system, which further simplifies the specification of control programs, right? If control programs are working on physical network, they have to worry about, all the elements, all the devices in the network. But if they're operating on a virtual view, then, like it is another layer of abstraction. It just simplifies how we express those programs. Is that clear? And there's a question. So are these events stored on the hardware or do they get triggered after match action? So, it is all up to specification, right? So if you want to store events, you have the options. If you want to, typically, if the events are occurring at a slower frequency and there is a reason for us to have a longitudinal view of that event, then you might want to store it. But a lot of time these events are transient and there is not a lot of value in storing these events. But like you can process those events depending on the requirements and type of programs that you want, right? And okay. All right. Okay. Sorry, here I am. Okay. All right. From API perspective, the Onyx is offering this global view as a network graph. The nodes represent physical network entities and the developers program over the network graph, right? So, like it has a node for a port, it has a node for host, and then, like you can express the programs on these. You can write, like go from node 1 to node 2. And then like, you're not just looking at these switches. Like a lot of time when we think of network topologies, we only break things down at the granularity of these networking switches and links, right? But it goes one level down and has a node for the specific port that is responsible for taking the packet from the switch to a particular host, right? So a switch, physical switch, it's, you can treat that as a forwarding engine, and then you have a port, then you have a host, right? So like, like it is a bit more detailed, and that allows it to independently say query information from different components, right? So this abstraction is important because it is interested in information from each of those elements in the network, right? So if it wants to know how many packets have have this port seen, right? So this is a counter that the port can maintain, and this is something that the program can register and say like, okay, I'm interested in the number of packets at this port, right? So it needs an abstraction for that port, and that is why the graph is a bit more fine-grained compared to a typical network topology graph that you would see. Okay. So Onyx network information base holds a collection of network entities. It can be viewed as a centralized graph with notification mechanism, and updates to this nib are asynchronous. So there is no ordering guarantee, and Onyx provides some synchronization primitives. I'll talk about it. But what does this really mean, right? So that there is a centralized graph with some notification mechanism. What does that mean? Can anybody tell me that, what do you think like this notification mechanism means when we talk about network information base? So I think we can try to visualize what's going on here, right? Because I think like this network information base is important to understand. So let's take a crack at that and try to see if we can explain this better. So I'm going to open up my visualizer so that we can check. You can see my, oh, you can't see my screen, right? Okay. So can you now see my notebook? Perfect. All right. So we are talking about the network information base here, right? So this is the operating system, right? And it is offering like a view of the network as a graph to control programs up there. Okay, so this is just a simple example of a graph, right? And this and we have a bunch of devices. So like let's consider that we have a topology of 3 or 4 switches down here, and then they are responsible for connecting hosts. And these hosts are the ones that are running some type of VMs, right? I'm not really good with these drawings, so bear with me. But if anything is not clear, I can like work that out. So let's try to draw some links here. Okay, so we can call this A, this is B, right? And we can call this as switch 1, switch 2, switch 3, switch 4. Okay, and there's some virtual switch sitting inside the host as well. Okay, so now when we have an operating system and we want to create the view of the network, right? So I'll keep this discussion a bit simple because like in general, Onyx also has the view from the port perspective, but let's for now assume that there are very limited ports. So the view of the network graph that we have is very similar to what we have here as the topology, right? So I'll try to make this very similar. So we have node 1, which is kind of like the virtual switch that we have on A. Then we have something here, then we have here, then we have something here, here, right? So this is virtual switch on A. Then we have 1, 2, 3, 4, and then we have virtual switch B. Is that like legible, right? You can see what I'm doing here, right? Okay, so this is the network view that we want to offer to the control program, right? So program 1, and maybe we have program 2 as well. Okay, so what does this program 1, program 2 really means, right? So I can have like tenant 1 with this type of VMs, and tenant 2 that is like offering these cross VMs, right? And this is something that we discussed before as well. So program 1 might only be interested in managing the network for the VM type 1, or like these crossed one, and the 2 will be responsible for managing the other set of VMs, right? So this is an example of that. You can have 2 different programs, and you can have this view of the network. So now I think somebody had question about so somebody had the question about the virtualization as well. So from virtualization perspective, if I am like offering the connectivity here for program 1, then I will only care about like I'll ignore this part. I'll ignore these switches, and I only care about A and B, and A and B connected to just VMs, right? So I think Garrett is asking that, doesn't the graph include ports? Yes, it includes ports. I'm simplifying the view of the network here. It also includes the host, right? So I should also say that, there will be 3 VMs attached here, right? So one will be checked one, and then something will be like crossed. Okay. Port I want to ignore because that's a level of detail that will just make things very complicated here. Okay. All right. So and then if I want to provide this virtualization, then I'll remove everything here for program 1. If I'm offering virtualization, then the network will look something like this. Oh, sorry. Right. So this is a virtual view of the network that can be exposed to program 1, but that will require a virtualization layer on top of network operating system, right? But I'm just logically providing that argument here. Okay. But when we say that we need this notification mechanism to make sure that the network information base is updated, what does that mean? So in this context, can anybody explain what does that mean? I think like some of you already attempted to answer about what does an event mean, right? So event, we can view event as a notification as well, right? So what will happen? So let me try to take one more step here. So suppose that an event happened where this link goes down. Okay, what will happen? What will happen is that when this link is going down, then there will be nodes will broadcast that message until it reaches. Yes, basically, like you can set up program which says like, if I see a particular link down, which a particular switch can detect that a link is down, it can send a message to the operating system saying that, hey, like, I think the link associated with this port is down. And 2 might also say that I think this link associated with this port is down. Then what will happen is that the operating system will take these set of notifications into consideration and then update the view of the network where it will take down this link, right? So now when we don't have this link, then the control policies have to be updated as well, right? So the control policy, like the control program maybe was routing this traffic via path 1, 2, 3. So it might have to reroute that path through 1, 4, 3, right? So this is a change in control program that might be triggered based on this updated view of the network. Is this making sense to you folks? Yeah. Okay. So now I'll talk something about the synchronization primitive as well, right? So what it says is that, if I want to make any changes to the network, right, there are 2 things that I can ensure. That, like, when I'm reading information from the network, then I'm just doing a read operation. Read operation does not require a lot of synchronization. Like, you just process all these messages and figure out that what is the most recent message, what is the latest state of the network, and update your state accordingly. But now when you're trying to push things, right, and there are multiple control programs in play, so it is possible that two control programs might want to make the same change, right? So like 2 control programs might say that, okay, maybe take all traffic to a particular node, or drop all traffic. Like there are a lot of possibilities in terms of how there are 2 programs that can write a conflicting rule. Now the question for the network is that how should it handle these type of conflicts, right? Should it provide some type of synchronization primitive intrinsically to the control program itself, that like maybe there is a lock that control program has to acquire and then push their rule down, and once they are done with their then they release the lock, right? So this is how changes happen in distributed systems as well, right? The other approach is that everybody just pushes their changes to the network and then, let it happen. If that's what they do, then it is possible that there is an inconsistency in the network, in a sense that, I can push something and there is someone else pushing something. There is a race condition that is happening. Whoever's update is the latest, that rule will be applied, right? So how is network handling these type of race conditions? So what Onyx is doing is that it is just simplifying this abstraction, saying that, we don't want to complicate things for the control programs. Let the race conditions happen, and rather than requiring these programs to have a lock or wait for acquiring a lock, we can push these updates in asynchronous manner, and then have a synchronization primitive in place, where each of these control programs will wait for a confirmation whether their rule has been applied or not, right? So if if, say, for example, program 1 is pushing a rule to the operating system, which is making some changes to this OVS, right? And program 2 also was pushing some other change, which was also pushing a rule to this OVS, right? And they are both writing some type of conflicting rules. Then what Onyx is offering is that it will provide a feedback saying that, okay, your rule has been successfully installed, or it will tell program 2 that your rule was not successfully installed, right? And these programs can, handle things accordingly. If program 2 that its rule didn't work, then it has to implement the logic of how it will handle the failure of execution of these control logic, right? But this is the primitive that Onyx, again, I'm saying Onyx, but Onyx decided to apply. And the at surface level, you might think that, hey, this is a bit too complicated, because all these programs have to reason about how they're going to handle the failures when their rules or the control programs that they're trying to push are not getting realized. But that's a design choice that they had to make, right? So one option is that you have this sophisticated, locking mechanism in place, where you just lock, place some locks and then ensure that only one entity or one program can make changes at any point of time. It just it is one abstraction, it has its pros and cons. This is another abstraction which has its pros and cons, and they chose the second one, right? Okay, so I think I've covered a lot of details for distributed systems, and distributed systems is not really the course I'm teaching, but at the same time, I think these concepts are important to understand, that what really are the challenges in building these type of operating systems. And I want to comment that it's not clear that this is the best design choice out there, and you have to take into perspective that a lot of time these design choices are heavily contextualized based on where these decisions or where these systems are going to get deployed. In some settings, the approach that they have embraced works fantastic, but it might not generalize for some other network settings, right? So it is not important to understand what Onyx did, but it is important to understand what is the design space, what choices did they have, right? So that's something that we should try to understand, and less focus on the specifics of the algorithms or systems that they embraced and used. Okay, so I'll switch back to slides now. But do you have any confusions for the part that we discussed so far? Okay, so as you can imagine, nib is the focal point of the system. State for application to access external state changes imported into it, and the local state changes are exported from it, right? So if there are some changes that are happening on some other control servers, then it is importing those changes from there. And if it is making some local changes, then it is exporting that information out, right? So this is what the nib realization on a particular control server is supposed to do. And of course, it has incredible scalability challenges. Of course, a single physical server won't scale. So nib will overrun the amount of memory that a one server can hold. So that is another challenge to worry about. CPU and bandwidth for one server will also not be able to handle all these updates. So this is kind of what we have been discussing about from design perspective. What Onyx particularly does is that it focuses on partition, which is that it decouples the switch state from forwarding state, right? So now this is interesting, right? So the switch state and forwarding state now are treated separately. That the forwarding decisions that you're taking, they are different from the updates that we have about the network, or the event updates that we have about the network, about like, what is the state of the switch? Is it active or it is not active? Is a port on a switch active or not active, right? So these are the switch specific state, and then we have the forwarding state. It partitions the forwarding state and assign each partition to an Onyx instance, right? So it is partitioning the forwarding part, and it is assigning that to the Onyx instance, and each instance is maintaining a consistent switch state, right? So each instance of Onyx has this consistent switch state, but the forwarding decisions of forwarding state is actually decoupled across or divided across all these Onyx instances for scalability purposes. And fast changing metrics such as link utilization. You remember I was mentioning about this metric called link utilization. So this can change a lot, right? So depending on how much traffic is coming in, what type of workload we have, the link utilization can change. So this is stored in distributed hash tables, and the control application, the metrics that are relatively long lived, such as the control programs itself. So they are pushed to a different storage, which is providing a bit more consistency guarantees, right? So think of Cassandra or systems like that. So they are used for the metrics that are not changing rapidly. And control applications are updating the local forwarding state, right? So the control applications are the one that are updating the local forwarding state, and then those those forwarding state information is pushed down to the local elements by this instance of the Onyx. Okay. And then it also leverages this principle of aggregation or abstraction of aggregation, that it leverages the inherent hierarchy that we have in the network topology, right? So hierarchy meaning that there will be, there is this pyramid-like structure. Think of the TOR that we have in the data centers. So right, we have a bunch of these rack of servers that have a top of rack switches that are connected to another set of switches, the L2 switches, and then eventually connected to the aggregation routers, right? So there is this inherent hierarchy that happens that is there in the network hierarchy. It just leverages that to offer aggregation and assigns instances accordingly. It shields the remote instances from the local updates, right? So if you have these hierarchical instances, then whatever are the local updates in some other device, you don't have to really worry about that, right? And it exposes a subset of elements in nib as an aggregate element to another Onyx instances, right? So rather than providing this really fine-grained view, it can abstract away the local details and provide a even more abstract view of the network to the other Onyx instances up in the hierarchy, right? And this can simplify the control programs that are operating at the higher levels, but then there is a bit of a compromise in fidelity that when you aggregate information, when you aggregate any set of information, then you're losing the fidelity of the information that you have, right? And that is happening in this case as well. So there are pros and cons of these type of approaches, especially when we talk about aggregating the information in the nibs. But that's a compromise that either you go with extreme fidelity or you go with scalability, right? So that's a design choice. It all depends on which type of setup you're going to deploy these networks in. And then there are these consistency guarantees. So as I was saying that, not everything requires consistency, and that has been the driving principle for the design of Onyx as well, that, a lot of these network operating systems will be operating on a lot of state that is transient, and there they don't really care about consistency, right? And or at least the durability, they don't care much about the durability, at least in that case. But control logic dictates the consistency requirements of the network state it manages. So there are two storage options. There are these replicated transactions, or the replicated transaction storage, that is mostly suited for the state that is changing slowly, right? So think about topology, that the topology can change over time depending on whether a particular link is down, whether a particular switch is down, but those events are relatively rare, right? Compared to the events where you are looking into the ones that are tracking, say, link utilization, right, or number of packet counters and stuff. So that is a more transient set of metrics or events, and for that it is using this one hop memory based DHT, but for the others it is using these replicated transaction storage, right? So control logic is resolves conflicts whenever necessary. So as as we were discussing before, that it is providing the synchronization primitives, and it knows that there will be conflicts that will be happening, but the control logic should be responsible for handling that logic. Okay. So Onyx instantiates software-defined networking's distributed state abstraction, right? It is an operating system. It is there to realize or instantiate the distributed state abstraction. These scalability challenges require embracing a distributed systems approach, and the lack of cleaner APIs for control applications has been a challenge in general when we design these things. And it does resolve consistency issues, consider scalability implications of control applications, but overall, it's not a perfect solution out there, right? So it is trying to do a lot of things, but at the same time, it is still requiring the control programs to be a bit heavily involved in the process, right? So as we were looking about how it is handling the consistency issues, so control programs are responsible for, then they're not completely detached from what's really going on in the network, right? So and that's a very fundamentally challenging thing to do at the first place, right? And that's kind of like something that comes onto the picture when we talk about these networks in general, that there is this, networks are all about distributed state. Now the question is, what is the right abstraction that we offer such that we can simplify the management or control of these devices, right? So whatever Onyx is offering in terms of APIs, it is okay. It is good for the time, and it is good for the requirements at that time. But we will discuss as we move forward that some of these problems didn't bore well as the requirements changed, and then they had to be resolved as we move further, right? So I think we are now coming to the end of this lecture, and it is possible that you didn't understand each and everything especially that we covered the last tail end of the lecture. So if you want, I can slow down and go through that last piece one more time, which is the specifics of the Onyx approach. But I hope that the high level message is clear to you, that we have these network operating systems that are helping us realize the distributed state abstraction. There are these inherent scalability challenges that the operating systems have to solve and address. And Onyx is a realization. It is addressing a few of them, but it is not addressing all of them, or it is not solving the ultimate problem or the ultimate view and vision that we had for software-defined networking, right? So it's a good intermediate step. It is solving a lot of problems, but it's not the perfect solution out there, right? And I would say there is no perfect solution out there. These are inherent problems that one has to worry about, but we can wiggle around a bit and think about maybe maybe we could have provided a better abstraction in terms of how we handle consistency issues, or maybe we could have provided some other better abstraction in terms of how we scale handling of these events. So different pros and cons, right? And we will keep discussing these issues as we move forward. But I hope the overall concept of the network operating systems, what they do, what different type of choices we have, is clearer at the end of this lecture. Any questions before we leave? Is quiz 2 open? So quiz 2 will be open soon. So quiz 2 release date is January 17. Yes. So quiz 2 should be open soon. I think I would say by end of today, the quiz 2 should be open. Okay.